My name is Jared Lettery, and I'm a reproductive endocrinologist and academic advisor for Fertility. We've established a curriculum in artificial intelligence and its intersection with ART, and over a series of lectures that we'll be presenting to you, hopefully will enhance our understanding about how this can improve outcomes for our patients. Our first speaker is Dr. Nadav Rappoport, who holds a PhD from the Hebrew University in Jerusalem. He's a perfect candidate for our first lecture. He's skilled and extremely experienced in machine learning, artificial intelligence, and its intersection with electronic health records. It's essentially what we're trying to do as we move AI forward within the ART space. I'm hoping that we'll walk away from this lecture understanding exactly what machine learning is, how it distinguishes itself from various other predictive analytics, and how it can move us forward for better outcomes for our patients. I look forward to your comments, Dr. Rappoport, and thank you so much for participating and contributing to our understanding of machine learning in general and how it can improve what we do every day in assisted reproductive technologies.
Hi, my name is Nadav Rappoport, and I'm an assistant professor at Ben-Gurion University of the Negev in Israel. My expertise are in the area of big biomedical data and machine learning application in healthcare. I would like to share with you some background and explain different concepts in machine learning and artificial intelligence. What will we talk today? First, we will non-formally define what is machine learning. Then I'll describe a few machine learning tasks or problems that can be appropriate for machine learning approaches. Then I'll describe how can machine learning model be evaluated. And I'll close the lecture with an example of specifics and families of machine learning algorithms. First, I would like to briefly explain some concept and basic terms. People are mixing and often use different related terms, and specifically artificial intelligence, machine learning, and deep learning. I want to give a sense and not a formal definitions. Artificial intelligence is a broad aspect of the world of AI, and it covers ethical issues, mathematical concepts, and proof. Machine learning covers algorithmic aspects as well as mathematical proofs of boundaries on convergence sign, required sample size, and more. Deep learning is an architectural family of algorithms of machine learning models. In this type of learning algorithms, the models can be represented as a multi-layer neural network where information passes through neurons to other neurons in order to make complex decisions. So first, let's understand, what is learning? There are multiple definitions, and one of them states that learning is a process of acquiring new understanding, knowledge, or skills by repeated experience. Notice that there are three main components here. First, there is a process. Second, there is a skill that can be evaluated or measured. And third, there is an experience. This is learning in general. How about machine learning? Neil Nelson, one of the world leaders in AI, said, a learning machine is any device whose actions are influenced by past experience. Herbert Simon, who won both Turing Award and Nobel Prize, said, learning is any process by which a system improves performance from experience and without explicitly being programmed. What do I mean by saying without explicitly being programmed? In traditional modeling, part of the modeling was to feed the algorithm the data and the rules for how to decide what should be the result for different types of data points. In the machine learning approach, the rules are not fed explicitly into the model, but rather are learned from the data. So in this way, the algorithm gets a sample of the data and also the expected result for every point in the sample data. Then the algorithm learns a model which it can use for unseen data points where it doesn't have its result. We will see example of such in a few slides. So to sum it up, learning is improving with experience at some task. So we have to have a defined task which we want to improve our performance. For the performance, we must have a measure that measures what are the performance, and we must have some experience. The field of AI started over 50 years ago. So why now there is such a hype and rise in machine learning? There are multiple reasons that emerge in the recent year. First, a serious advance in machine learning algorithms. Second, a huge increase in computational power, and especially due to GPUs. Third, there is a tremendous amount of data available to train such models. In general, we can split the machine learning algorithm to 3 types according to the required task: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, we have a label that a model needs to predict. In unsupervised learning, we have no labels. And in reinforcement learning, the model can act on the world. In supervised learning, each example has a label, and the task is to predict the labels. Or in other words, the input is pairs of observations and labels, and we want to learn a model that, given a new observation, predict the label. Let's see a few examples. The first type of labels are binary. In such classification tasks, we need to predict whether an example belongs to the first class or to the second. Let's think of an algorithm that accepts an email, and then it needs to decide whether this email is a spam or a legitimate email. F here represents the mapping function from the example to the label. X is the example, and Y is the label. The examples or the instances can be represented by multiple properties, which we call features. For example, for an email, we have its length in words, the number of recipients, and whether it has an attachment. The labels we want to learn to predict is whether an email is a spam or a legitimate email. Here is an illustration of the learning process. We have a collection of samples which can be used to train the model. The algorithm gets the data and output a classification model. Now that the model was trained, we want to use it as a predictor. When we get a new sample, when we get a new sample, so an email and its properties, we want to ask the model to classify it to one of the 2 classes. If the model thinks it's a spam, then our mailing service will put it in the spam folder. Otherwise, it will put it in our inbox. Another example for supervised classification is to classify the grade of an embryo based on its image. Supervised learning is not limited to classification tasks, but also for regression tasks, where we want to predict a continuous range of values. For example, the Framingham risk score is a known clinical risk score for cardiovascular disease. The user needs to enter a few clinical parameters like age, sex, and blood pressure, and then you can get the risk in percent for MI in the next 10 years. To conclude, the 3 types of supervised learning. Binary classification, where the label is binary, meaning it can be one out of only 2 options, like true or false, spam or legitimate email. The second type is multi-class classification, where the label is one out of multiple options. For example, when we want the model to label what objects are in a picture. A third type is regression, where the label to predict is on a continuous range, like probability for a future event or expected yearly revenue. A different type of machine learning is called unsupervised learning, where there are no labels to predict. If so, what can a machine learn? Think of it as follows. We have many observations. Each observation has information, properties, features. Here, for example, we have label data, and for each observation, we have different features. Each column is a different type of feature. We can learn to cluster close samples together, or we can identify outliers, or we can learn how to reduce the space for sample representations. also called compression or dimensionality reduction. I'll shortly describe each of these types. In clustering, the task is to assign each sample to a cluster where close observations are assigned to the same cluster and unrelated samples in different clusters. There are different flavors of clustering, and the number of clusters may also be part of the learning task. In anomaly detection, we want to learn possible patterns in the data and identify samples which look odd. For example, detecting cyber attacks using unusual network communications. The third type of unsupervised learning is called dimensionality reduction, where we want to represent complex objects using smaller space or a smaller number of parameters, but still be able to keep most of the information. It is useful, for example, when we want to reduce bandwidth or use some type of algorithm which are limited by the number of parameters it can handle. Here is an example. The original data is in 2 dimensions, though we can rotate it and keep only 1 dimension while still preserving most of the variations in the original data. How can we evaluate performance of a trained algorithm? For example, we want to compare the performance of 2 algorithms. There are many types of evaluation metrics which are adequate for different tasks. For regression tasks, we want to measure the distance between the prediction and the real label. This can be done using mean absolute error, which is the average of the absolute distances of all samples. Or we can use the mean squared error, which is the average of the squared difference between the predictions and the true labels. Or the root mean squared error, which is the squared root of the mean squared error. For classification problem, we can use accuracy, which is a fraction of correct classifications. Other metrics that can be used are sensitivity, specificity, positive predictive values, and more.
Another metric that is used only for binary classification is called ROC AUC. The area under the ROC curve, or in short, ROC AUC, is broadly used to evaluate the performance of binary classifiers. The ROC curve plot illustrates the trade-off between the false positive rate and the true positive rate for different decision thresholds. What I mean is that when our classifiers output a value which is a probability or its confidence that one sample belongs to the first class or to the other, we can binary the prediction using the threshold. For different threshold values, we can get different values of false positive rate and true positive rate. This trade-off is plotted in the ROC AUC, in the ROC curve. As the area under the curve is larger and closer to 1, it indicates that the model has a better discriminative power.
In unsupervised tasks, we don't have the true labels, but we can still measure the performance. In clustering, we can measure to what extent the cluster we define are homogeneous. Or we can summarize the distances between observations in different clusters and compare it to distances between observations in the same cluster. When we do dimensionality reduction, we often use the distance between the original observation and the reconstructed observation based on the compressed version. In machine learning, we are concerned from a scenario where the algorithm will learn something that is too specific to the training data it used, and therefore the performance we estimate will be over-optimistic. This phenomenon is called overfitting. In the right plot, you can see a regression model that has a very low error, and it passed through all samples. But actually, it looks like an overfit, and a better model will be the regression line on the left. To test whether a model overfit the data, what is usually done is to keep aside a portion of the data, let's say 20% of samples, that are not used to train the model. This test set is only used after the training phase to estimate the performance of the model. If the performance of the model on the test set are far from the performance of the model, if the performance of the model on the test set are far from the performance of the model estimated on the training set, then we may suspect that the model overfit the data. Let's see a few examples of machine learning algorithms. There are many algorithms for different tasks. For regression, common models are linear regression or polynomial regression, where we try to fit a linear function or a polynomial function to the data. Here in the example of the right, the data is of 2 dimensions, and I try to fit a linear line, which is the red one, or a polynomial function with a degree of 3, which seems to fit better. For binary classification, we can fit a logistic regression, which is a linear model with a logistic transformation or a decision tree. Another algorithm that can be used for supervised learning is called KNN, K nearest neighbors. In this algorithm, given a new sample, it looks for the K nearest samples in the data, and then it uses their labels to predict the label of the new sample. For unsupervised learning, there are other algorithms. For dimensionality reduction, a famous algorithm that uses linear combination of features to generate new features is called PCA, which stands for Principal Component Analysis. For clustering, there are several algorithms. For example, K-means. In K-means, first you need to define how many clusters are there, and then the algorithm looks for optimal assignment. Another clustering method is based on agglomerative clustering. This is an iterative model where in each iteration, it merges the closest 2 samples or clusters until it reaches a point where there is a single cluster. Using machine learning is not only plug and play, and there are many challenges and things to try when developing a machine learning model. Data extraction, preparation, and cleaning may be often challenging. How to generate features using the raw data requires prior knowledge and understanding of the data. Selecting the appropriate algorithm and right hyperparameters can also change the results. For example, we talked about K-means algorithm and the K-nearest neighbor. In these 2 algorithms, one needs to decide what K to use and how to define the distances between 2 samples. And of course, selecting the evaluation metric can have a direct impact on the learning as it affects the optimization function. To sum up, we saw 3 types of machine learning tasks: supervised, unsupervised, and I mentioned there is a 3rd one, reinforcement learning, which we did not call. In supervised learning, we have some true labels, which we want to predict, and the labels can be of a binary natures, categorical, or continuous. In supervised learning, we have no label to predict, but we want to learn about the structure of the data or the relationships between the samples. Here we also talked about 3 types, which are clustering, anomaly detection, and dimensionality reduction. We mentioned that it is important to be able to measure to what extent we learn. So we gave few examples of performance evaluation. In supervised learning, we can use accuracy, precision, recall, ROC-AUC, and others. In unsupervised, we can use the distances between examples to measure the performance. We only touched the surface of a few machine learning algorithms. We mentioned that in supervised learning, we can use linear regression, decision trees, and K-nearest neighbors. In unsupervised learning, we can use PCA, K-means, agglomerative clustering, and of course, many more. Thank you for your time, and I hope you learn new things. Now, I'll be glad to take any questions.
Dr. Rappoport, that was excellent. You understated the issue when you said that you're scratching the surface. These are incredibly complicated topics, and your explanations were spot on, enough that I think the viewers and participants could get a taste of what's going on. and what's out there. I'll see if there's anyone posting questions, and if not, I have a few that I can pose to you myself. So to keep the conversation going, one of the very practical aspect of assessing these algorithms and the tools as they roll out will be for a potential user to assess really the quality of the algorithm, whether or not it's going to work. What would your advice be to somebody who's not well versed as you are in these topics of machine learning? What should that person, whether it's a clinician or an embryologist, look for in evaluating these potential tools?
Yeah, so this is a very good question. And I think that here a clinician or a caregiver has his or her point of view. So what is more important for this specific task? Whether he's more important in the recall, or maybe the precision is more important in this specific task. So you know, me as an AI expert can give an algorithm, but then you tell me, okay, I would prefer to increase the precision, and we can fine tune the model in order to try and achieve this goal.
Asaf will be talking about literature and how to interpret the literature. But one of the things that I'm finding in just reviewing potential manuscripts is there's machine learning in every title of articles that come out. What's the acid test that a reader could look for to determine whether or not the algorithm described in the manuscript is a true machine learning tool?
So when I think that when someone critically try to read such a publication, so first of all, you need to ask himself whether this was shown as in a single site or a multiple site. It make a huge differences. It was shown that often models that will train on a single data set, on a data set from a single clinical center, are not transferable to others. And when they try to transfer it to another institute, the performance drop significantly. So I think this is one of the main concerns. So if something was shown to work, you know, on a multi-site and was validated on using external data set, this is I would call it a higher quality model that I would try and implement maybe in my institute.
Yeah, excellent. There's a couple of questions posted. What is the best practice? I'll read these to you, Dr. Rappoport. What is the best practice in comparing performance of different models based on different studies, papers, with different data sets? You've kind of touched on that, but perhaps you could elaborate a little bit further.
Yeah. So it depends on the task, right? So we talked, for example, on supervised learning, where we have several measurements that we can compare the measurement itself. So if there are, let's say, two different models, two different work, publish the precision or the recall or the OKUC, we can compare these values and say, okay, this one is better or this one is better. Of course, we need also always to keep in mind that maybe there is different, inherently different maybe in the data or in the context where it was performed. So maybe in one hospital the performance was better because the population is more homogenic, and in another hospital the performance were lower, but the population is heterogeneous. So this is for supervised learning. For unsupervised learning, so the performance are more complicated. I mean, it's more of an art of feeling the data and feeling the performance, showing that, and often you don't stop on the classification, but you are taking it a step forward and asking, okay, let's say I found there are 3 clusters of a diabetic person. What characterize each of these cluster?
can I see something which is clinically relevant in every cluster? Maybe those are just say younger than those, or maybe those have more complications, or things like that.
Excellent. Another question posted: how do you think the field of machine learning will continue to develop? And a corollary question posted: can we trust the models that are out there today?
Okay. Okay, I'll answer the second one. I think it's easier. Can we trust the models that are out there? So it depends. Okay, there were papers which showed that models that were already implemented in hospitals are not showing the performance they expected. It was a paper, I think, published only a few weeks or maybe a few months ago in New England Journal of Medicine, that they show that prediction models that were integrated into a hospital, into a set of many hospitals, were not showing the performance that they promised. Okay, and I think you need to be very careful before you implement and integrate such a model into your data. But there are this was, of course, one example, a very big example that showed that other models do have an integration, a successful integration, and show, improving performance and the workflow of the physicians and save lives. So this is the common case. And you also ask some more broader question about the future of AI, and I want to take it into future of AI in the clinic. And I think that more model will be used, will be trained, will be published, and will be integrated into the clinic. And I don't think AI will replace human caregiver, physicians in the near future. Okay, they are going only to improve the workflow, improve the diagnostic, improve clinical decision, and support clinical decisions, but not replace physician, human physician. Human physicians are required, are needed, and are here to stay. Okay, me as a patient, I want to talk to a human being.
Yeah, I think that's an excellent point. Part of what we'll be facing up ahead is to convince both patients and caregivers that artificial intelligence in the clinical setting is a safe bet, that physicians aren't going to be replaced, but in fact, these tools will augment the ability to make precise decisions that are updated literally day to day. I think one of the earlier references you made was to a tool to predict the likelihood of sepsis in intensive care that turned out not to be as advertised. And I think this was actually a CE mark approved item. So it's extremely complicated. You take the hypothetical trial and it seems to work. And as you expand its use, the reality may be quite different.
Yeah.
Excellent. More questions from the audience? Well, this is excellent. I so appreciate your time. It's really great to have someone bring in the hard engineering analytical side to what we do every day, and that is try and help people build families. So thanks so much for your time and insights.
My pleasure. Thank you for hosting me.
Yes, great. Look forward to meeting you in person.
It's a pleasure.
Good, we can end now. Thanks all.
Okay, bye-bye.